In this video, I would like to demonstrate how you can create a dual model for a linear programming model. I'm going to use a product mix example. So here we have a model that optimizes profit, maximizes profit, subject to three resource constraints where we have to decide how many units of two types of products to make. And the variables are also non-negative. So you see total profit is this function, and the resources are these three constraints and resource constraints. And each of them is less than or equal constraint. And if you solve this problem using some kind of solver like Excel or Gurobi, you're going to get an optimal solution which will tell you that you should make 122 units of the first product, 78 units of the second product. The total profit is $66,100. And you also get sensitivity information like shadow prices, and you get slacks, and you also get reduced costs for decision variables x1, x2. Both of them actually happen to be 0. So how can we create a dual model for this problem? So first thing we're going to do is this. We're going to multiply each constraint by a positive or non-negative multiplier, right? Both sides will be multiplied by y1. Here, both sides will be multiplied by y2, and here both sides will be multiplied by y3, right? So both sides of this constraint, both sides of this constraint, both sides of this constraint. Well, assuming that all, I'm going to save this, all yi's are greater than or equal to 0, right? If this was less than or equal, after multiplying by a number that's positive or 0, it's still going to be less than or equal, right? If it's 0, it's going to be equal, obviously, but if it's positive, it should be less than or equal to, right? And so if I do this, I'm not really changing the constraints except for multiplying them by a coefficient. If I add them, then, right, if each individual constraint holds, then the summation of the left-hand side, and it should be less than or equal than the summation of the right-hand sides, even after multiplying by those coefficients. So what am I going to get? Let me write this down. I'll have y1, actually let me write this in black, y1 times x1 plus x2 plus y2 times 9x1, x1 plus 6x2 plus y3 times, from the third constraint, 12x1 plus 16y, 16x2, right? That's the summation of the left-hand sides after they were multiplied by those positive or 0 multipliers. And this, right, has to be less than or equal to 200 times y1 plus 1566 times y2, and from the third constraint, 2880 times y3, right? I hope it is clear that this should hold if the constraints hold and if the multipliers are greater than or equal to 0. Okay, now I'm going to rearrange the terms here. I'm going to observe that x1 is here, x1 is here, and x1 is here. I can actually take all the terms related to x1 and put them together and then multiply by this summation by x1. And then the same thing for x2. I can observe x2 is in these three places. So what will I have if I take all the x1 terms? I will have y1 plus 9 times y2 plus 12 times y3. And this is all multiplied by x1. What do I have for x2? I have y1, again, 1 times y1. I have 6 times y2. And I have also 16 times y3. Right? And this is all multiplied by x2. And obviously it is still less than or equal to 200 y1 plus 1566 y2 plus 2880 y3, right? Now let me observe another thing. If I compare this function that you see here right, the left-hand side of this inequality, to the objective, right? Here the objective is also something times x1 plus something times x2, and the same thing here, right? When will this function be greater than or equal than the objective? Well, if this part, let me use another color, if this part is greater than or equal 350, and this part is greater than or equal 300, then this function that I see here, right, is going to be greater than or equal to 350x1 plus 300x2. Right? So provided that these two hold, so this is another restriction, right? I had a first restriction here, 1. Then I have a second restriction, which is here 2, right? Provided that this holds, and provided that this holds, this part that you see here, right? I can say this is greater than or equal to what? To 350 x1 plus 300 x2, right? If this part is at least 350 and this part is at least 300, and notice the variables, remember originally I assumed they are greater than or equal to 0, so everything is positive here, right? Then if this multiplier is 350 or more and this multiplier here for x2 is 300 or more, then it should be greater than or equal than the original objective, right? But what I want you to see is, right, so if this is the objective, right, the original objective, it has to be smaller or equal to this, and this in turn has to be smaller or equal to this part, right? Then this part is an upper bound on the original objective function, right? So this is an upper bound on the original objective function. So suppose I would like to minimize this original objective, this upper bound, right? If I have an upper bound, it's like an upper estimation. If it's very high, I'm not very happy with it because it's weak. If I can lower it, I could have some kind of information that's interesting, right? I would say, well, how high can this total profit be? If it can be 1 billion, that's not very interesting because it's probably way overestimating. But if I could lower it as much as possible, I can find a very interesting value. So what I'm going to do is I'm going to take this, right, this upper bound value, and I'm going to try put it as an objective of a new model. So I'm going to say minimize 200 y1 plus 1566 y2 plus 2880 y3, right? So this is some kind of new objective, but it's minimization. The original one was maximization. And I said this is going to be an upper bound, right? This is going to be an upper bound on the original objective function value. However, under certain conditions. What conditions did we put? Remember, we put 2 conditions, right? Let's start from the second one. We said that, right, so there are conditions. y1 plus 9y2 plus 12y3 must be greater than or equal 350. That's this condition here, right? This first of those conditions, number 2, first part of it, right? And the second one is this function must be at least 300 y1 plus 6y2 plus 16 y3 greater than or equal 300, right? And this is condition number 2, but there was also condition number 1. We set all the variables y, so let's list them here now specifically. y1, y2, y3 must be at least 0, right? Greater than or equal to 0. Okay? So what I would like you to see is actually that this model is using all the numbers that you saw in the original model. However, what was before on the right-hand side, 21566 to 2880, is now in the objective coefficients. What was in the objective, 350, 300, is on the right-hand side. And what was in the, as the coefficients of the decision variables, they are now the same, except that the coefficients in the A matrix, except they are transposed, right? What was in the rows, 1, 1, 9, 6, 12, 16, is now in the columns, 1, 1, 9, 6, 12, 16, right? So this is a model that actually uses the same data. However, it kind of is transposed, right? So we had before 2 decision variables and 3 constraints. Now we have 3 decision variables and 2 constraints. What's interesting is if you solve this problem, you will obtain the optimal solution of this problem. The optimal solution, right, of this problem is going to be, right, y1 star, y2 star, y3 star is going to be surprisingly 216.67 and 0, right? And I want you to see, what is that? These are exactly the same numbers as shadow prices in our original model, right? The same numbers that are obtained for those dual problem variables, optimal values, are shadow prices in my original model. If you look at optimal objective function value, is going to be 66,100, exactly the same, right? So now I want you to see, this was the value of the original problem, and this is going to be the same value in the dual problem, right? So the values of objective functions are actually exactly the same, right? What's also interesting is if you notice, if you look at shadow prices of this problem, right, there'll be shadow prices and slacks, right, or slack. So shadow price of this first constraint is going to be 122. Actually, let me put it in a different color to make the message clear. 122 and 78. And notice the shadow prices here are the same as the optimal solution in the primal problem, right? And again, if you see slacks here, 0 and 0, these both of those constraints will be binding, right? They have non-zero shadow prices, so they must be binding. They must have slack 0. They are equivalent to the reduced costs. These values will be the same as the reduced costs here, right? So these are interesting. These are interesting equivalences. What else? We might notice that what was a slack in the original problem will be reduced costs in the new problem. So if you look at reduced costs in this problem, will be 0, 0, and 168, right? Again, right, there is an equivalence. What was slack here is a reduced cost in this problem. So this is an interesting pair of problems, right? This first original problem that we defined here, actually I should maybe exclude this part, this right? This was the model, of course, without the multipliers, right? This problem we could call primal problem, right? This one was the primal problem. Okay, let's circle it, right? And this problem that we created here, the new problem, right, is called the dual. Maybe again this circle, right? This is called the dual problem. So this is an interesting equivalence that if you take a primal problem in linear programming, you can always create a dual for it. The dual will give you the same objective function value as the primal, and then there will be these equivalences, the main one being that whatever shadow prices you have in one problem are the solution of the other problem.